Hello everyone. Let's revise work, energy and power unit. A bus is traveling at a constant speed of 6.2 meters per second along a section of road that is inclined at an angle of 6 degrees to horizontal. The bus is represented by the blue dot shown below. Draw a labeled sketch to represent the force acting on the bus. So we have the weight, downward direction, and we have the normal force perpendicular to the slope. As the bus is moving along the slope upward direction, we have thrust or engine force, and then we have a friction force opposing the motion. State the value of rate of change of momentum of the bus. Rate of change of momentum is a net force, right? So as a bus is traveling with constant speed, the net force equals to 0. And the Newton's second law is net force is proportional to rate of change of momentum. If the net force equals to 0, as the bus is traveling at a constant speed, then rate of change of momentum also equals to 0. B. The total output power of the engine of the bus is 70 kilowatt and the efficiency of the engine is 35%. Calculate the input power to the engine. So output power is given, efficiency is given. The question is asking the input power. So we use efficiency formula. Efficiency is output power divided by input power. That means input power equals to output power divided by efficiency. Output power is 70 kilowatt divided by efficiency 0.35. That gives us 200 kilowatt. The mass of the bus is 8.5 times 10 to 3 kilogram or 8,500 kilogram. Determines the rate of increase of gravitational potential energy of the bus. The question is asking the power, right? The output power actually when the bus reach the position after a second. We see that in every second the bus travel along the slope 6.2 meters. So that is the distance traveled or distance over time. That's the hypotenuse. Height is height per unit time. Here is the same time. So sine theta equals to opposite over hypotenuse. So opposite is height per unit time and opposite is hypotenuse per unit time. Height gained per second equals to height per second equals to hypotenuse per second times sine theta. Hypotenuse per second is 6.2 meter per second times the sine 6 degree. So that gives us 0.648 meter per second. The question is asking the rate of increase of gravitational potential energy. So power equals to energy over time. Energy at the location is gravitational potential energy. So gravitational potential energy per unit time. And we can rearrange. Mass is 8.5 times 10 to 3 times gravitational field strength is 9.81 times height per second or height gain per second is 0.648 meter per second, and that gives us 5.4 times 10 to 4 watt. So using your answer to C and the data in B, estimate the magnitude of the resistive force acting on the bus. engine power supplied equals to useful power to climb the height plus the power used to overcome the friction. We can express this way. Engine power equals to useful power to climb a height plus the power used to overcome the friction. Engine power provided 7 times 10 to 4 equals to useful power 5.4 times 10 to 4 plus the power used to overcome the friction. And we can find power used to overcome the friction equals to 7 minus 5.4, which is 1.6 times 10 to 4 watt. And power equals to force times the velocity. In this case, power used to overcome the friction equals to frictional force times the velocity. And the frictional force equals to power used to overcome the friction divided by velocity. So that is 1.6 times 10 to 4 divided by velocity, which is 6.2. That is 2.6 kilonewton or 2,600 Newton. E. The engine of the bus suddenly stops working. I. Determine the magnitude of the net force opposing the motion of the bus at the instant at which the engine stops. The moment the engine of the bus suddenly stops working, we have reaction force perpendicular to the slope, weight downward, and the friction force. We also have the horizontal component of the weight, which is W sine theta. The component of the weight down the slope equals to mg sine theta. Mass is 8.5 times 10 to 3 and acceleration due to gravity is 9.81 sine 6 degree. That gives us 8.7 times 10 to 3 Newton. So the net force equals to friction force plus the component of the weight down the slope, which is friction is 2.6 times 10 to 3 plus the component of the weight down the slope 8.7 times 10 to 3 Newton. So total is 11,000 Newton or 11 kilonewton. I discuss with reference to the air resistance the change in the net force as a bus slows down. As we know, the drag force is proportional to velocity squared. Drag force decreases or air resistance decreases as speed drops. Therefore, net force decreases. A. Outlines the meaning of a work. So work done is a force times the distance moved, and the distance moved is in the direction of the force. So let us visualize that. We have a wooden block and applied force is F, the red one. And horizontal component is F cosine theta. So we move the block to a distance of S. And we have distance traveled S. So the work done is equals to horizontal component of the applied force F cosine theta times the distance traveled, which gives us Fs cosine theta. So work done is a force times the distance moved in the direction of the force. B. Some cargo ships use kites working together with the ship's engine to move the vessel. The tension in the cable that connects the kite to the ship is 250 kilonewton. The kite is pulling the ship at an angle of 39 degrees to the horizontal. The ship travels at a steady speed of 8.5 meters per second. When the ship's engine operates with a power output of 2.7 megawatt. I calculate the work done on the ship by the kite when the ship travels at a distance of 1 kilometer. So, the tension force applied is T. And the horizontal component of tension is T cosine 39 degree. And the work done is the force times the distance in the direction of the force. So the distance traveled is S equals to 1 kilometer, which is 1000 meter. So work done is the force times the distance in the direction of the force. So that is F times S times cosine theta. So the force is 250,000 Newton. Distance traveled is 1000 times cosine 39 degree. And that gives us 1.9 times 10 to 8 joule. Shows that when ship is traveling at a speed of 8.5 meter per second, the kite provides about 40% of the total power required by the ship. Let us find the power provided by kite. That's the tension, as we know, and the horizontal component is T cosine 39 degree. And we know the power formula, which is F times velocity. In this case, F is T cosine 39 degree. Velocity. So we have the force parallel to the velocity. So the parallel component of tension is T cosine 39 degree, and times velocity, which is T cosine 39 degree times velocity. That gives us 25,000 times cosine 39 degree times the velocity 8.5. That is 1.7 times 10 to 6 watt. So the total power equals to the power of the engine, which is 2.7 megawatt, and power of the kite. So the total power equals to 2.7 plus 1.7 times 10 to 6. That is 4.4 times 10 to 6 watt. The question is asking the fraction of the kite's power. So fraction provided by kite equals to power of the kite divided by total power. And the power of the kite is 1.7 times 10 to 6, and the total power is 4.4 times 10 to 6. That gives us 0.38 or 38%. C. The kite is taken down and no longer produces a force on the ship. The resistive force F that opposes the motion of the ship is related to a speed v of the ship by F equals to k times velocity squared, where k is a constant. Shows that if the power output of the engine remains at 2.7 megawatt, the speed of the ship will decrease to about 7 meters per second. Assume that k is independent of whether the kite is in use or not. So power equals to force times velocity, and force equals to k times v squared, and times v, that gives us kv cubed. That indicates that power output is proportional to velocity cubed, or velocity equals to root cube of power. or third root of power. And we can apply proportionality. V1 over V2 equals to cube root of P1 over P2. Let us substitute values. P1 is 2.7 times 10 to 6. The P2 is 4.4 times 10 to 6. We found this in previous slide. That gives us 0.85. So V1 over V2 equals to 0.85. And we know V2 velocity 2, that is 8.5. And the final result is 7.2 meter per second. D. The ship's engine are switched off and the ship comes to rest from a speed of 7 meters per second in a time of 650 seconds. I. Estimate the distance that the ship takes to stop. Assumes that acceleration is uniform. We know the initial velocity from the previous slide, that is 7.2 meters per second. The ship's engine are switched off and the ship comes to rest. So final velocity equals to 0. And the time taken is 650 seconds. So we use acceleration formula. Change in velocity over change in time. Final velocity is 0 minus initial velocity is 7.2. Our time taken is 650. That gives us a deceleration of 0.011 meters per second. Then we use timeless formula. Final velocity squared equals to initial velocity squared plus 2 times acceleration times displacement. Displacement equals 2. Final velocity squared minus initial velocity squared divided by 2 times acceleration. Let's plug in the values. Final velocity squared is 0 squared minus initial velocity squared is 7.2 squared over 2 times the acceleration minus 0.011. And that gives us 2,400 meters. II. It's unlikely that the acceleration of the ship will be uniform given that the resistive force acting on the ship depends on the speed of the ship. Using the axis, sketch a graph to show how the speed v varies with time t after the ship's engine are switched off. We know the initial velocity is 7.2 and the engine is switched off. So after 650 seconds, the engine stops and it is decelerating, so we should expect a changing velocity. Or we also know that unlikely the acceleration of the ship will be uniform, so we get a graph that the decreasing gradient and eventually stops.